Ladies and gentlemen, we are now moving into Chapter 2, Low Temperature Solar Thermal Power. The learning objectives for this chapter will be: number 1, to understand the principles of flat plate solar collectors. Number 2, to know the difference between unglazed and glazed flat plate solar collectors. And number 3, to understand the working principle of vacuum tubes, also called evacuated solar collectors, Sydney tubes, heat pipes, Chinese collectors, etc., etc. So the content of this chapter is basically low temperature solar collectors, unglazed solar collectors, glazed solar collectors, evacuated tube solar collectors, and then we moved into the fundamentals of flat plate solar collectors. Basically, we'll be looking at the components of a flat plate solar collector. The heat balance involves the thermodynamics. In flat plate collectors, we are going to use a single cover collector as an example. Good. Talking about low temperature solar collectors, we basically have these three types: the unglazed solar collectors, the glazed solar collectors, and the evacuated tubes solar collectors. The following slides will tell you more about these collectors. For unglazed solar collectors, they are typically used for solar pool heating. They have a dark absorber plate made of either metal or polymer. An unglazed flat plate collector, that an example is very simple. You have a water hose that you leave out in the sun, and there is water in it. So when you come to empty the water, after some time, you will see that the water is warm. It's nothing but an unglazed solar collector. Another example is to put a bucket of water under the sun, and after some time you come and pick the bucket of water, you will see that it is warm. It's simply an unglazed solar collector. So here on the right picture, you see coils like hoses. Okay, so water is being run through them, and water is heated up and sent to the swimming pool. Another one here on the left picture, water is being run through them and sent to the house for use. So basically, they don't have any cover, either plastic cover or glass cover. They don't have any cover, and we don't perform any selective coating on them. There is no frame like a box where you put them inside. There is no insulation. So they are very simple. But at the same time, they are only efficient when the output temperature is near the ambient temperature. That is, if the outside is even warm. in temperate climates during the winter, these collectors will not simply work unless summertime. Now, for glazed solar collectors, they work on the principle of the greenhouse effect. What is the greenhouse effect? As simple as that, just raise the windows of your car, close the doors, and leave your car under the sun. For some hours, you come back. When you open your car, the inside is warmer than the outside. So, it's simply the greenhouse effect. The greenhouse effect is based on the fact that glass will allow certain radiation within a certain wavelength to pass through. But once these radiations enter and they meet matter, like inside your car seats, your board, etc., etc. So these radiations are being absorbed by matter, and therefore matter heats up. And when matter heats up and start radiating back, they are radiating back in what we call the longer wavelength radiation. That is thermal radiation. And thermal radiation, fortunately, or unfortunately, depending on the situation, thermal radiation or longer wavelengths are not able to pass through glass. So therefore, thermal radiation is trapped inside your car. So let me come again. The glass allows certain radiation to come in, and once the radiation enters the car, the radiation heats up matter, and matter tends to release back the radiation in the form of thermal radiation, which lies in the longer wavelength, of the spectrum. But these longer wavelengths are not able to escape because glass does not allow them to go through. Consequences: the inside gets warmer and warmer. That's why when you leave your car in the sun, you come and open the door, you enter, inside is very hot. It's the greenhouse effect. How does that relate to global warming? You see, CO2, when you release it, and other gases like methane, they travel to the atmosphere, and then they form a layer and behave exactly like the glass in your car. So solar radiation is able to come through, gets to the earth, heats up anything that it meets on the earth, comprising you and I. But when we decide to radiate back that radiation in the form of thermal energy unfortunately is not able to pass through. Consequence: the earth is getting warmer and warmer, and people are worried. People said, if we get to some point the ice onto the deep sea will melt, the climate will change, the patterns will change, and we'll be in trouble. So this is greenhouse effect. So now, that's the bad effect of greenhouse. But the good effect, we are using that phenomena in solar thermal collectors. So what we do, we get a box, okay, and we cover it with a glass. It could be also a plastic. It has also that property. So, and solar radiation comes in. It heats up anything that it meets inside the box. To enhance this, you can coat the inside, special coating that absorbs much of the solar radiation. Normally it's being coated black, because black is being said to absorb much of the radiation. And then when it heats up and it turns to thermal radiation, the thermal radiation is not able to go back. When it comes, it meets the glass, it bounces back, goes again, it bounces back. So it's a sort of imprisoned in the box. Consequences, the box, inside the box, it gets warmer and warmer. This again is being illustrated here. So where you have the sun radiation in yellow colored coming through the glass, heats up anything that it finds, and then the heat here is being radiated back, but unfortunately, that's the red lines. Unfortunately, it's not able to go through the glass. So it's then confined inside. So this principle, when you understand it, is underlying principle behind solar collectors, thermal collectors. Good. So basically, glazed flat plate collectors are used for domestic water heating, air heating for drying, etc., etc. So an example of flat plate solar collector for water heating is the picture on your screen. So you have the box being insulated on the back, okay, to avoid heat being conducted to the ground where it is seated. You have the glass cover on top. You have the flow tubes. This is for water heating, so you have the flow tubes inside in contact with the absorber plate. So the heat is being transmitted into the tubes, into the water in the tubes. So water comes in cool and goes out warm. Now, what is evacuated tube collector? So, look at the picture on your screen on the right. This is a typical tube. This tube here is made up of actually two tubes, one inside the other. So imagine this is a tube and you get another one you put inside, but in between the two there is space. And the space, you make sure it is emptied. There is no air, there is no matter inside. And you make sure you seal it. So you have one tube being concentric on the other, and in between them there is space. This is what you see here. Okay? So, and your absorber is sitting in the emptied space. This, why the empty space? The empty space will reduce the heat losses because you are collecting heat. And as you are collecting more heat, the difference in temperature between your absorber inside and the outside air will be bigger and bigger. And as this temperature difference gets huge, but the losses also go with it. So to reduce the losses, so here we create the vacuum. And you know, convection cannot take place without matter. And because you have created a vacuum, you have therefore taken off any heat losses through convection and even conduction, because there is no matter. Good. So these tubes here, you use many of them to form a solar collector. Here you can count the number of tubes here. There are many. Now, the configuration in which you use them, there are two basic types. You have what we call the direct flow, and you have the heat pipe. How does it work, the heat pipe? This is the tube. This is the tube. So, and inside you place a heat pipe. So if you don't know what is a heat pipe, just read about it. It's a simple device in which you have a fluid. The fluid is confined. It's a closed loop. It's not open. And at one end of the pipe, is warm and the other end is cold. So assuming you heat up the fluid here, the fluid will evaporate and become vapor, and the vapor will then rise slowly to the top due to the difference in densities. And when it gets to the top, you just need to find a way of taking the heat away, and then the vapor will condense and come back here, and the process is repeated. Okay. So the copper header that you see on the right picture here, you have, for instance, water coming in cold. The blue color means that the water is cold, and it goes out warm. That's the red color. By picking the heat on top of this one. So in summary, you have two fluids. One fluid confined in the heat pipe, being inside the tube. This is the tube, the vacuum tube, and you put the heat pipe inside, and then you have the second fluid, which could be water, coming on top here, and picking up the heat and goes away. And each time it picks the heat, the liquid inside here becoming vapor on top here, we could then condense. And because the tubes are always inclined, you don't put them flat on the ground. So once they condense, they will flow down by gravity. That's why evacuated tubes are always inclined at an angle. At times, it's advised to incline them about 30 degrees or 45 degrees. This is to allow the condensed vapor to come back in the form of liquid. Good. So the picture on top here is simply the one down, but for aesthetics reasons, the copper header is covered, and then there is insulation. It looks like a foam, okay, to avoid the heat losses. And then this one is made nice, okay. You don't know what is happening. You just need warm water, okay. That's all. Good. The direct flow is illustrated in this picture. So instead of having a heat pipe, you rather have a flow of a liquid coming in and then picking up the heat inside the evacuated tube, the vacuum tube, and goes out. So this is a cross section of this one. So basically you have this other type where instead of having a form of a U tube where the liquid comes in and goes out, the liquid comes into the center and flows back, okay, and flows back on the extremities, okay, as outlets. And this is a cross section of this one. So a picture here gives you the direct flow, this very type, okay. You could see one copper tube going inside and one copper tube coming out, and they are all built in the evacuated tube. They just go and pick the heat and go away. There is something very important that I would like to mention, that if you look at the evacuated tubes, they have some sort of nips, and they have different colors. These ones here are special materials that they paint inside, and these materials, because the tubes are going to be working, normally their lifespan is about 15 years, 15. So, and because of the coatings, you have created a vacuum, right? But heat with some coating will generate some gases with time. So your vacuum with time will no longer be vacuum. So this special coating here is made in such a way that any gas that is being formed inside the vacuum is captured by these materials. So they are there on purpose. Good. So one improvement of the evacuated tubes is the compound parabolic concentrator. It actually combines the two effects, concentration and then evacuated tubes. So you have the evacuated tube on at the center, and you have a collector. It looks like quarter of a cylinder. You have a cylinder, you cut it at a quarter. And you have one here, 1/4, another one here, another quarter, and they are mirrors. So the sun radiation comes and hits the mirrors, and they are reflected right onto the evacuated tube. This actually enhances the heat collection. So the normal evacuated tube here can give you temperatures of about 160 degrees, while this one can give you about 250 degrees. It's because of the concentration that enhances the concentration. Good. Let's look at very closely the components in a flat plate collector. So basically you have the housing, that's the casing, you have the insulation, you have the heat transfer medium, you have the absorber, the black line, and then you have the transparent cover. The transparent cover, as I explained, it allows the radiation with a particular wavelength to pass, and then it captures its energy. That's the absorber. The absorber captures the energy of the radiation. But the glass cover will not allow the radiation emitted by the absorber to pass in the opposite direction. So that's the main function of the glass or plastic, the transparent cover. So another function that goes in doing that, because it is covered, you make sure it is sealed, airtight, so air will not come in. Okay? So in that matter, if there is even wind blowing on top, the wind will not pick up the heat and go away. So the glass cover here reduces then heat losses at the same time. So there are two different coatings, treatments that you do to the glass cover. On the outside, you put an anti-reflective treatment so that when the sun radiation comes in, it will not be reflected back, because you want it to go through. And the second treatment you need to do, you do the opposite treatment inside, on the inner side of the glass cover. So you rather enhance the reflective property on the inner side of the glass cover, so that when the absorber radiates its thermal energy, it will be reflected back inside each time. It will not go. Good. The absorber. The absorber is that part of the panel that picks up the heat of the solar radiation and converts it into usable thermal energy on a fluid current using convection and conduction mechanism. So basically the absorber here should have a very high absorption coefficient. Should absorb as much as possible the solar radiation. And then it should emit less. It should not emit the radiation. Because though the glass cover is treated so that it will not allow the emitted radiation to go through, it's not 100%. So you have an absorber made of a substance with very high absorption coefficient, but at the same time very low reflective coefficient. The insulation prevents conduction heat losses, the insulation of the casing. Okay, so you make sure the insulation is made up of a material that can withstand high temperatures, because in these collectors you get temperatures above 150 degrees Celsius. Okay. So in summary, you have the glass cover. It should be tight, should be made up of a material that is either glass or plastic. It should be airtight. It should also allow, it should not also expand much with temperature, because you see, if it is because the temperature is being heated up and it can easily expand, and during the night when the temperature goes down, it will contract and we let air to come in. So the glass cover should not be that expansive type of material. So the insulation should also be airtight, waterproof, should not allow water to go in. It should also be airtight, should be able to resist high temperatures. Now let's look at flat plate collectors and look at the heat balance, the thermodynamics involved. So there are a number of assumptions. I'm not going to read all of them. They are on your screen. And the number one very important assumption is the performance is being carried out. All the calculations that we are going to see, they are being carried out in steady state mode. And another important assumption is that the heat flows in one-dimensional direction. It is not true, but it's an assumption to make life easier. Okay. So basically, if you look at the absorber, the solar radiation being absorbed, that we call Q dot abs, is also equal to E dot opt, and is equal to the useful heat. The useful heat is what we are going to take for either heating your water or any other purpose that you want to do. That's the useful heat. And then you have the losses. And inevitably, you have some heat that is being stored inside the absorber that you cannot extract. That is normal because of its heat capacity. So in summary, you have the useful heat, you have the losses, and you have the heat being stored, all equal to the heat that is being absorbed. That's the first law of thermodynamics. Nothing is lost, nothing is created, all is transformation. So the energy that is absorbed by the absorber, they are in three forms: the useful heat, the losses, and the heat being stored inside the absorber. Good. So the absorbed heat can also be expressed like this. IS is simply the solar radiation coming in. ASD is the surface area of the absorber. You multiply it, but the solar radiation always comes in terms of watts per square meter. So when you multiply by the surface, you get watts. And these two dimensions, the tau is the transmission of the glass cover, and alpha is the absorptance of the absorber. These two parameters, they are all in between 0 and 1. So if you have a transmittance of 98%, it means that 98% of the solar radiation can go through that glass cover. And if you have an absorptance of let's say 98%, it means 98% of the solar radiation can be absorbed by the absorber. It's as simple as that. Now, the useful power. The useful power, if you are using it to heat up a fluid, okay, T out is the temperature of the fluid at the outlet, and T in is the temperature of the fluid at the outlet. If you multiply it by the mass flow rate, m dot, and the heat capacity, then you get the useful heat. This relation is quite elementary, and I'm sure you know it. And then the losses. The losses are in three forms. Heat transfer losses are either conduction, radiation, and then convection. The three can coexist. But basically they have their own formulas. But basically all the losses can be lumped together and give this formula. Remember your heat transfer courses? So we can define an overall heat transfer coefficient that involves the radiative heat losses, conductive heat losses, and then convective heat losses. And AC is simply the collector area. So the heat being stored in the collector is given by this formula. And when you are dealing with steady state means it is constant with time. So dt will be equal to 0. So you can then ignore the heat stored in the collector when you are doing your analysis in steady state. Steady state, it does not change with time. So all the parameters with respect to time remain constant. So dt will be equal to 0.